Welcome to the next lecture. In this lecture, we will be concentrating or we will be trying to understand how Fourier analysis is going to help us understand computer vision in depth. Okay. So how many of you have already worked on Fourier analysis? You might have studied in your engineering mathematics or in any other related courses. What do you understand by Fourier analysis? What is a Fourier series? Can anyone tell me what is a Fourier series? We are open to discussions. We are open to discussions. In Fourier transform, we are going to represent a signal as a weighted sum of sinusoids. You know what is a sinusoid function? Any function that varies in this format, right? Any function that varies like this. Okay, this is a sinusoid function, and when it begins from 0, sine 0 is 0, so we call it a sine, and if this begins with cosine, it looks like this, the other way around. That means here it begins from 1. So f of x is equal to sine x, a function of sine. Okay. So how we are going to convert this? We are going to convert our image into a series of weighted sum of sinusoids or cosines. So we are going to imagine our image to be a wave. Instead of pixels, instead of dot pixels, we are going to convert this into waves, and we will have spatial frequency. Spatial means the distance from one point to the other, or in general as space. Okay, I am teaching you from the basics. I want you to be very cautious, and very difficult to understand in certain places. And if you have any clarifications, you are always free to ask me anytime. Okay, so we are going to convert this into spatial domain. We have two domains now. One is called as the spatial domain, and the other one is the frequency domain. So why do we need to do that? What is the reason? That's why I put it as intuition. Fast changes in an image correspond to high frequency components, and slow variations correspond to low frequency components. So in around 1890s, Fourier said that any periodic function can be expressed as a sum of sine and cosine components. Okay, each with its own frequency and amplitude. So these are the two terms that you have to keep in mind, that is about frequency and amplitude. So this is the introductory basic slide for you to understand how we are going to convert images into Fourier transforms. So what about non-periodic waves? Okay, so here we have Fourier transform, sine and cosine waves which can be converted as Fourier transforms. So Fourier transform is a method that represents the variable as a summation of complex exponentials. So what you can see on the screen is a function of this. See what you see in the bottom here. This one is the sum of first these waveforms. Okay. We are converting an image into wavelets. Okay. So we'll be understanding the Fourier's idea 1807. The periodic functions are represented as the weighted sum of sines and cosines. Initially, like for all the great scientists, when Fourier proposed this, people did not take it very serious. They never thought that it could change the entire way we do all kinds of programming or all kinds of domains. Not only in computer vision, but in almost all cases of transformations. We are using sine and cosine waves. Therefore, Fourier transforms applications are almost universal and global. So now we have seen linear operations. Fourier transform is a linear operator that maps a functional space to another function's space and decompose a function into another function of its frequency components. You have to remember that whenever you study Fourier analysis, you have something called as this amplitude A and frequency F. In general, any wave can be expressed in terms of amplitude. Amplitude means is the number. Frequency is the number of times a thing is repeated. I am telling you frequently something means from that is what frequency has been derived. Frequency means number of times a thing is being repeated. Okay. How frequently I called your name inside the class. That means that the number of times I have used your names. Same thing applies here. Frequency is the number of times it is being used. More technical terms, in signal terms, number of times a signal crosses from positive to negative is called as its frequency. Number of times a signal crosses from positive to negative is called its frequency. Understood? Amplitude is the number that is being denoted, the height. Suppose this is a sinusoidal wave. This stands for amplitude A. And number of times this is crossing from this to this to this is its frequency. Is it clear? All of you understood? Okay. So we are going to change our basis. Okay. This is a mathematical change of basis where new basis elements are converted as complex sinusoidal functions. So an image, we are going to break it down into sine and cos components. So here how it happens, low frequencies are those where you have smooth gradients and broad shapes, high frequencies, sharp edges, finite details, and so on. Okay. So the basics of Fourier analysis in images is that instead of looking into image as a grid of dots or pixels, what we are doing is that we are considering this to be overlapping waves. Okay, so why do we want to do that? We want to do that because we can edit it more easily. We can edit it with much higher speed. Complex calculations can be broken down into very simple calculations and can be more effective when it comes to fast Fourier transforms. We'll see what it is. So JPEJ can save your space. Initially, you can see that all your images require a lot of space. You do some kind of compression, you do some kind of reduction without changing the quality and so on. You do some kind of transformation to keep your images stored, saved so that it can easily be accessed by you at any time. Okay? So now this is the Fourier analysis. S of x is the output where this is a function of x, where f is the frequency and phi I is the phase. Okay, f stands for frequency and phi I phase. Okay, so now another one important thing I will teach you is convolution. A convolution operation which we have already seen convolution while we were studying about linear filters. I know how many of you remember that? How many of you remember the convolution operation we studied while we were learning about linear filters? So what is convolution? Very simple, explained here in very simple terms. We are considering the signal OX. OX is the output after convolution of h of x, which we consider it to be the impulse response. Here we have given this impulse response h of x and this s of x. The output should be a sine omega x plus phi naught. Phi naught is the phase. So here omega is equal to 2 pi f. Okay. 2 pi frequency. Omega is the angular frequency. Angular frequency means what? What do you literally understand by angular frequency? Lateral means straight, angular means motion in rotation. Okay. So how many times it rotates? So this is called as angular. Everything that is linear or lateral, you have something angular also. Okay. Are you all able to understand? Any queries? So now we have seen S of x, S of x, convolution, h of x, that's giving us O of x. So in terms of signals, you have a signal here S of x, which is a sinusoidal signal. Here you're convolving it with a impulse signal. This is an impulse signal, right? Impulse signal, and the output, the Fourier OX, OX, which is equal to A sine omega t plus phi naught. Okay. This is how this signal is represented. So two types of Fourier transform which we can cover in our syllabus or which is required for our computer vision applications. The first one is Discrete Fourier Transform, DFT. The Fourier transform in its discrete, you have two types now, one is continuous and discrete. See, a continuous waveform is represented by S of t. Here I'll write it as S of t is equal to A sine omega t minus theta or something like that. Okay, this thing is a continuous signal. Here, S is the amplitude and omega, you know, is the angular frequency or 2 pi f. Omega is equal to 2 pi f or the frequency in simple terms, and this theta can be the phase. Okay, so any signal is represented in this manner, and this is a continuous signal, and this is represented like this. Okay, now we have its discrete form. The same signal can be represented as Sk of n, say for example, is equal to A sine omega n minus theta. So here n means discrete points or discrete point of time. Here what we are doing is that we are converting the sine wave into discrete samples. Okay, instead of having it as a continuous sine wave, what we are having is we are having discrete points like this. Okay, so these are the discrete points. Now let us consider we are going to transform one from one form to the other. Okay, so we have here UV as the output. Okay, U and V, L, M. Okay, what you're going to do is that your image is of the form L, N, M, and you are going to transform it as L, U, V. Okay, and it is not continuous, it is discrete. What we are seeing is how we are going to work with discrete transforms. Okay, how we are going to do that? We are using this general formula for, that is L, that is L n comma m e raised to minus j minus 2 pi j into un by n plus vm by m. This is the way we are going to convert the quantities of the image, which is in terms of n comma m, into sinusoidal and cosine forms. Okay, so this is called as discrete Fourier transformation of an image. Noted down? Any questions? Any queries you can ask me. So whatever I explained to you, I simply wrote it in a mathematical form. Okay. So this is N M is converted to U and V. Okay. So UV is the Fourier transform of L M. Now what is 2D discrete Fourier transform or 2D DFT? What we have seen in the previous is for a single dimension you had only X. Now here the same thing for a two-dimensional. Whatever we have seen is what we are repeating again. You have M and N, an image, a digital image of the size Nm, which is a function of X and Y, is converted into another domain, which we call it as frequency domain. So we are using 2D DFT to convert something you have in spatial domain to frequency domain. Okay, that is something that is of the term xy is converted to uv. F of x comma y is converted into f of u comma v. This is in spatial domain and this is in frequency domain. I am repeating these points and I am going much slower because this is the foundation for your computer vision. This is the one with which you may need to do your projects in future. So that's why I want you to study well and give your complete concentration here. Okay. Next point is inverse of that. You have converted from spatial domain to frequency domain. Now inverse discrete Fourier transform, you are converting from frequency domain to spatial domain. What you are doing is the other way around, from frequency back to spatial domain. See, after initial set of transformations, what we are doing is that we are converting it back to the original form. And these are the very common ways with which you can convert your images. Transform, save it, use it and reuse it. All your image processing is done using Fourier transform. Have you heard of DCT, discrete cosine transform? I believe that all of you would have studied these things in your basic mathematics. Fast Fourier transforms. One of the biggest disadvantages of discrete Fourier transform is that, one of the biggest disadvantages of discrete Fourier transforms is that it is a highly complex. That means of the order of mn square. Order of mn square for a m cross n image. Okay, so here it takes around 17 trillion operation for a 2048 into 2048 images. This means that the width of the image is 2048 and the height of the image is 2048. If you want to transform this using your discrete using your discrete Fourier transform, you need to have around 17 trillion operations. So what we are doing is that we wanted to reduce the complexity. For any program to be very successful, it should be having less computational complexity. More the computational complexity is there, less efficiency is the project or the program. So for that, what we have done, we have invented something, we have discovered something called as FFT algorithm, Fast Fourier Transform, which is reducing the complexity from mn square to om. So what is meant by convolution theorem? A very small simple theorem. Convolution in spatial domain is equal to pointwise multiplication in frequency domain. A very simple theorem. I hope you can understand, because I believe that you know what is convolution. So this theorem will be the basics or will be the fundamental tool for analyzing filters and accelerating complex image processing. So do you have any questions so far about the Fourier analysis of images, fast Fourier transforms and discrete Fourier transform? Can you tell me what is the disadvantage of DFT? Anybody? Why do we want to go for FFT? If